Hello, Royals. Part of lesson 3.2 on rationalizing denominators involves simplifying radicals. And normally we get practice doing this when we are solving the quadratic formula at the grade 11 level, no longer looking for approximate values for these. If we are in a semester where we had to trim a lesson, usually one of those lessons that gets trimmed is a review of the quadratic formula. So some students might find that they are at lesson 3.2 and they haven't practiced simplifying radicals. So I've just thrown together the worksheet 3.2.1 for us to practice on. And I'm going to walk you through a couple of those examples and show you a few different things that we need to be able to deal with. The expectation at this level is that we can simplify these expressions by hand. Some of your calculators, if you type in the square root of 12, will spit out the simplified version of the square root of 12. Other calculators will give you a decimal approximation. I'm not interested in knowing if you can type it into your calculator. And for that reason, when you see questions like this on an assessment, you will be asked to simplify by hand and you will be asked to show all work. Getting the answer will earn you 0 marks. You need to show all of your steps to convince me that you're doing this by hand. Okay? So when we look at something like the square root of 16, 16 is a perfect square. We write it as 4. We can see this if we write the factorization of 16 as 4 times 4. It is a perfect square. 12 is not a perfect square, but if we look at it carefully by looking at its factors, say 2 and 6, 2 and 3, we can tell that there is a perfect square factor of 4 in there. There's a couple of ways of doing this. Most of the time, students are able to see the factor of 4. So we can write the square root of 12 as the square root of 4 times 3. Now we're going to use a property. It's not quite distribution. It's just saying that some people might call it distribution. I don't. I say that the power of a product is equal to the product of powers. You can check this with other numbers to convince yourself that it's true. Try the square root of 36 being the square root of 9 times 4 is the square root of 9 times the square root of 4, which is going to be 3 times 2, which is 6. We know the square root of 36 is 6. So yeah, that statement's true. You try doing this with a sum, like the square root of 16 plus 9, which we know is the square root of 25, which we know is 5. Is that equal to the square root of 16 plus the square root of 9? Of course not, because the square root doesn't just distribute through. I don't know why we would assume that it would. Right. The reason why we wanted to write this as the square root of 4 and probably put the 4 first is because I know that the square root of 4 is 2. And then the only thing I need to be careful about is making sure that I write this 2 nice and big. There is an invisible 2 over here, right, in the square root symbol. I want to write this as 2 times the square root of 3. This will be helpful if I'm expected to, say, simplify the square root of 12 divided by 2. The square root of 12 divided by 2 is not the square root of 6. There's no factor of 12 in the numerator. A factor of 12 would have a factor of 2. This is the factor of the square root of 12. Well, if now I know, and I'd be skipping a bunch of steps here, I suppose. If I know that the square root of 12 is equal to 2 times the square root of 3, now I see a factor of 2 in the numerator. And I discover that half of the square root of 12 is actually equal to the square root of 3. Okay? Show these steps by hand, please. It's not going to take you that long to show all of them. The other way of doing this, let me show you with the 18. If I want to do a prime factorization of 18, I see it's 2 times 9. This one's a little different because I kind of see that 9 is a perfect square. But what if I wrote it as the square root of 3 squared times 2? Then I would be able to write this as the square root of 3 squared times the square root of 2. And what's the square root of 3 squared? Well, that's just 3, isn't it? The argument here is that sometimes it might be good to sort of keep our numbers smaller before they get larger. Another argument, though, might be that you're looking for the largest perfect square factor. If I look at 72, for example, I might see that 72 is 2 divided by 36, which is 2 times 18. So I see a factor of 4. I can ignore the fact that I saw 36, which is a perfect square. So I could write this as 4 times 18. I write that as the square root of 4 times the square root of 18, which is going to be 2 times root 18. But just like reducing fractions, I want to reduce these radicals all the way. And I believe that 18 still has a perfect square factor in there. 18 is 9 times 2. That gives me 2 times the square root of 9 times the square root of 2, which is going to be 2 times 3 times the square root of 2, which I should usually tidy up to 6 root 2. Notice we should have been able to see this maybe a little bit faster. I'm not going to need much room for this question. If after my first removal of a prime factor of 2, I see that the square root of 72 is the square root of 36 times 2, which is going to be the square root of 36 times the square root of 2, which is going to be 6 root 2. So I should be able to get the same answer even if I factor it in a different way. This is because there is only one way to prime factor any number. Now, just like some fractions can't be reduced, some radicals can't be reduced either. And you might be surprised by some relatively large numbers. It doesn't matter how big the number is, there still might not be a perfect square factor. The reason why I'll be confident that root 30 can't be simplified is when I look at the prime factorization of 30. I see that 30 has a factor of 2 and 3 and 5. That means that root 30 has a factor of root 2 and root 3 and root 5. None of those are perfect square factors. So this just can't be simplified. No simplification. Saying root 30 is the best that I can do. Okay. That was some examples like example or question 1 on page worksheet 3.2.1. Let's look at examples like question 2. There's one example that is a root 2 times a root 6. And I want to show you a couple of ways of doing this as well. Up here, I said that the square root of 4 times 3 is the square root of 4 times the square root of 3. So some students here will say, okay, well, the square root of 2 can't be simplified. The square root of 6 can't be simplified. 6 is just 2 times 3. There's no perfect square factors. So I'm going to write this as the square root of 2 times 6. They might even jump to the square root of 12. And I'm going to argue against this approach because what I've done is I've made my number larger. Some students won't see the disadvantage because they say, well, sure, but at least now I see a perfect square factor of 4. I'm going to try to show you that we should be able to find a perfect square factor of 4, or at least 2 factors of 2, if we make our numbers smaller first. But this is okay as long as my numbers don't get crazy here. Let's try it like this. If you write the square root of 6 as the square root of 2 times the square root of 3, this is all just a multiplication, right? You could put brackets here if you want, but they're not doing anything. This is all just root 2 times a root 2 times a root 3. And this root 2 times root 2, that'll be root 2 squared, or root 4, or 2. You might want to get used to just seeing root 2 times root 2 is 2. That's how we're going to be rationalizing in the lesson. Wasn't that faster? I'm still showing all of my steps here. If you were nervous, you could say this is root 4 times root 3, which is 2 root 3. I find this useful when I have something like 5 root 7 multiplied by 2 root 14. Okay, you could do that this is 5 times root 7 times 2 times root 14, which is 5 times 2 times root 7 times root 14, which is 10 times the square root of 7 times 14. And 7 times 14 is going to be 70 and 28, so 98. And I've made my number larger, and now I need to look at the factors of my larger number. Well, 98 is an even number. Half of 98, half of 100 is 50, so half of 98 is 49. So I get 10 root 49 root 2, which is 10 times 7 times root 2, which is 70 root 2. I'm not sure why I find this satisfying in a way. I don't know. Well, this seemed to take a little bit longer than it should have. This is not the recommended approach. In general, we should not make our numbers larger before they get smaller. even though root 14 doesn't really simplify, if I can see root 14 as root 7 times a root 2, then when I multiply things together, and I'm just choosing to change the order of my multiplication here, multiplication is commutative. It doesn't matter what order I multiply these things in. I see that I get a 5 times 2, which is a 10, a root 7 times a root 7, which is a 7. What's the square root of 7 squared? I don't need to know what 7 squared is. What's the square root of 167 squared? I don't know what 167 squared is. I don't know what the square root of 167 is. But I know that the square root of the square of 167 is 167. And that demonstrates understanding. Just multiplying because you can doesn't demonstrate understanding, and it'll make your job harder for you, especially if you don't have access to a calculator. Fine. Not recommended. Not a good approach. This right here is inefficient. Okay, make your numbers smaller before they get larger. Quite. And there's one other type of question, a sec here, where we are expected to sort of add mixed radicals. There's an example, I think, in question number 3 that looks a little bit like the square root of 12 plus the square root of 27. And this reminds me a little bit of doing 1/12 plus 1/27. Because I can add these expressions. They are like terms. They're both just constants, but they're not in a format that I can add them in. The square root of 12 plus the square root of 27 is not the square root of 12 plus 27. Okay, you can check it on your own again with examples. I did a counterexample of this. Choose something like the square root of 9 plus the square root of 16 so that the sum of your numbers is also a perfect square. Notice that that is not equal to the square root of 25. So what do we do? Well, it's almost like finding a common denominator, except you're trying to find a common radical. If it'll happen, the difference is that you can always find a common denominator. You can't always find a common radical. The way that we're going to add these is we're going to simplify them first. The way that we're going to simplify them is by looking for factors. So it still comes down, or once again, it comes down to factoring. And if you needed to identify what type of factoring, this is probably closest to common factoring. It's just monomial factoring, numeric factoring. This honestly will go faster without a calculator as well. You could just try to type this expression into your calculator and it would spit out an answer. But if you're working by hand, I hope we don't need to access a calculator to figure out that 12 is divisible by 4. There we go. So upon closer inspection, looks like root 12 and root 27 can both be written as multiples of root 3. And now if you read this in English, you'll understand why this isn't going to be something like 5 root 6. That's just nonsense. You have 2 root 3's, and to that you add 3 root 3's. So I'm collecting these things called root 3's. If I have 2 of those root 3's and I add 3 of those root 3's, I will have 5 of those root 3's. Some people like seeing a common factorization step here of root 3, and what I'm left with is 2 plus 3, which means I'm left with root 3 times 5, which is a little bit awkward to write because it looks like it could be root 35. I could write that, but usually we would say that the root 3's are the things that we're counting, and 5 is how many of those things that we have. So like fractions, you can manipulate your denominator, your count of the things that you are collecting. But just watch out for cases where you won't be able to find a like radical. Something like root 18 plus root 3 minus root 8. Root 18 is root 9 times 2. Root 3 is a prime number, so I'll leave that there. That's a 1 root 3, by the way. Root 8 I can write as root 4 times 2. This is going to give me root 9 times root 2 plus a 1 root 3 minus a root 4 times a root 2. Root 9 is 3. Root 4 is 2. So I have 3 root 2's plus 1 root 3 minus 2 root 2's. All of these are like terms. They're all just constant numbers, but these are not like radicals. 3 root 2's plus 1 root 3's isn't 4 root 5's. It's not 4 root 6's. It's not 4 root anything. They don't share a common factor. You wouldn't be able to remove a common factor and add your coefficients together. But 3 root 2's minus 2 root 2's, that can be simplified. 3 root 2's minus 2 root 2's would be 1 root 2. So this is the best that I can do in this expression. The simplest that I can, or the most simple format for the expression root 18 plus root 3 minus root 8 is 1 root 2 plus 1 root 3. You could write it as root 2 plus root 3 if you like. I like seeing the coefficients of 1 because I've seen students, if you give them like a root 5 plus a root 5, this is where they really panic and start doing stuff like root 10. Root 5 plus root 5 is like saying x plus x. Same argument with x plus x. A lot of people get confused with x plus x. They start saying that it's x squared. Well, if you write it and read it as 1x plus 1x, then you hear that it's 2x. If you say 1 root 5 plus 1 root 5, you'll hear that you get 2 root 5s. Okay?